for the French effort. And hello to everyone who's following the conference on YouTube or Slack. So I'm going to talk about a multi-species capture-recapture model to study synchrony and departure from stopover sites. This joint work with Pierre-Yves Henry, Daniel Turek, Emmanuel Cam, and Roger Pradel. So let's go. So as a short introduction about bird migration, we need to know that migratory birds travel each year between breeding and wintering areas. You can see some of the flyways on the right picture. But this travel is impossible to vision with a single flight of thousands of kilometers. So birds need to stop and refuel to be able to do the next flight. So as a consequence, more of 70% of the overall time of migration is spent on stopover sites. Something important is what can influence bird behavior at stopover sites. So Yan Schaub did a great review about that, and just listing many aspects of what can influence the bird behavior. But here we will focus on what can influence the departure decision from stopover sites. The studies from the past 20 years focus mostly on weather condition on one side, and then body mass and energy stores on another side. So we'll focus on this here. So something to know is that there's not only one species at stopover site. You can have 5, 10, 15 species stopovering at the same place because of favorable feeding condition. But our main question was, do these different species behave the same regarding departure decisions? So do they synchronize departure, for example, as on the figure below, with the departure probability of 2 species? So we'll focus on 3 species depending on reed areas. So the sage warbler, the reed warbler, and the blue throat. These 3 species weigh around 10 or 15 grams, and perform each year long-distance migratory flight. So let's now talk about the data set. So we have multiple years of bird ringing at 3 different sites, around 3,000 individuals. So the 3 sites are in France. So for example, my background is one of these sites, just reed areas close to the sea, which is also 3 pass trend depending on reed areas to limit the bias for birds going out of the capture area. And we took weather data from a meteorological station close to ringing sites. So let's now talk about the methods. So we used an open capture-recapture model with 3 main parameters. We have phi, the probability to stay between 2 days, with 1 minus phi is departure probability. We have the recapture probability at day, and eta, the probability to enter in the stopover area if you're not already entered. So for those who are non-familiar with capture-recapture modeling, we have the observation, the data we have with 0 and 1, not seen and seen. And the thing we want to infer is the true presence of the individual. For example, the birds could have arrived before the first capture and maybe depart after the last capture. These 2 processes are linked by a Bernoulli trial with a recapture probability. So let's now just focus on the true presence on the individual, or you can move from one day to another. It's also a Bernoulli trial with 2 main parts. We have the left part with the phi and z. So if the bird is already arrived in the stopover area, the left part applies and is equal to phi. And then if the bird is not already entered in the stopover area, it is the right part that applies and then is equal to eta. So it's simple, it's just phi or eta, depending on the bird is already here or not. So let's now talk about how we measure the synchrony for departure probability. So we used random effect, as in Grosbois and Laws-Montfort did about seabird survival. We have one common random effect term, delta, and one specific to each species. So for here, our parameter of focus parameter is phi, and then we have just alpha one intercept, and then delta plus epsilon. If we want to add a covariate, we just have, for example, with the linear effects, you can just have beta of the slope and then the covariate, the value of the covariate. These two random effects are normal distribution with variances, so sigma square delta and sigma square epsilon. But these variances are going to be really useful to measure the synchrony. For example, here we'll use the intra-class correlation coefficients. This is the measure of synchrony here. And then we'll just have to divide the variance of the common random term, sigma square delta, by the total variance. So sigma square, the variance of the common random term plus the one specific to the species. So this will result to a value between 0 and 1, measuring how the common random term captured the variation of departure probability. So we implemented this using a nimble, which were here way faster than JAGs. So yeah, really useful to use nimble here because without any specific parameterization, we gained a lot of time. So talking about the results, here I'm showing 1 year on one side about so the three species, the sage warbler, the reed warbler, and the blue throat. So we can already see that there's some peaks of departure probability, which seems to be almost the same between the species, and this kind of wave peaks around the month of August. And then if you're looking at the results and the ICC, we have already we have the values between 0.6 and 0.9. So this is values with high that shows high synchrony between species in the departure probabilities. So what are the underlying processes generating synchrony? This is really important to know because this is the question behind just after regarding if species synchronous departures. What are the processes generating synchrony? So we're going to use the variances, sigma square delta, and testing two more models with covariates. So we have the time since arrival and weather conditions. So the time since arrival will be used as the predictor of the departure probability and also the weather condition. And our main results here is that around 80% of the synchrony is generated by time since arrival. And this is really important here. So as a conclusion, we can say that reed passerine synchronize the departure from stopover areas, and that this synchrony is mostly generated by the time since arrival. So we can think that is something that a proxy of one internal state, maybe energy reserves. So birds need to stay a certain amount of time before replenish their reserve and then be able to do the following flight. But this could be verified maybe with mass data or body condition data. Something important also that our model is flexible because we can maybe add a large number of species and also add another random effect, site dependent, if the experiment is cope with that. So we can measure spatial synchrony and departure probability, for example. So this could be extended in many ways. And yeah, I'm going to just repeat again about nimble, just because I already worked on this kind of model without synchrony at the beginning of my PhD. And sometimes the computation time it was too long to be able for me to test many different scenarios or many different things. So yeah, Nimble helped me a lot. So thanks everyone for your attention. I hope you enjoyed this talk and enjoyed the conference, and thanks for the organizing committee of the ISAC for the great job on this first virtual conference. Thanks.